No. So, hello everyone. And for today's seminar, we have Antonio Marca. Antonio has been close friend, and he started his studies in Naples with me. Then he moved for his master thesis in Groningen, working on dwarf galaxies in the other one clusters. And actually, that work was discovery of first nuclei galaxies in the clusters. Then he moved for more 4 years in Netherlands, in Groningen for his PhD, working on the link between galaxy morphologies and supermassive black hole. And then starting from November 2025, we started this doctoral fellowship and the European Space Agency. It is in Leiden, and where we will expand this work done during the PhD with the UV dataset and other multi-wavelength facilities. So, additional to this is a colleague of one of the nuclei working packages, specifically the one on the nuclear observations with Euclid. And today is going to discuss about his work during the PhD and also inside for the future work that he will be doing in the fellowship. Antonio, you have 45 minutes. The floor is yours. I will give you 5 minutes warning.
Okay. So thank you a lot for the presentation. Thanks a lot. I'm a bit older than you. This is like you started studying while I was studying. Let's put this in context. And now thank you a lot for inviting me, Michele, all the team here. It was great. We always talked about it, and I'm very happy this happened, especially now before Marco is doctor, so I can still make fun of him. But yeah, I'm gonna try to squeeze in 45 minutes what I did in my 4-year PhDs in Groningen. Here, just my supervisor. I really like to acknowledge them because I was very lucky with Ling Yu, Wang, Scott Traeger, and Michael Bill. They were really great. And I think we were discussing yesterday with Marco, I think supervisor is the #1 component for a nice and successful PhD, and then hopefully career in astronomy or in science, whatever. So what I'm trying to give you is a bit of context on when, where, and how these supermassive black holes are fueled in galaxies. But before doing that, let's see if this works. Maybe it doesn't. Let's see. Is it on?
Yeah.
Yes. Yes. Okay. Cool. Just a quick table of contents so you can follow what we are going to talk about. And as I mentioned, I will try to give an introduction to put everyone on the same page to try understanding what we studied. Then I will talk a bit of common data and methods because this is going to go through my 4 years PhD. I use some data sets and some methodologies that are common for my work during the year. So I think it's nicer to have a single section with all data and methods. And then we look at the results that I try to divide into what we did in the local universe, so what we say redshift below 1, and then results at higher redshift that were possible thanks to the launch of the new facilities like JWST, so the James Webb Telescope, and Euclid in the second half of my PhD, and try to wrap up with some bit of discussion, conclusions, and if I have time, hopefully talk a bit what I'm doing right now. So let's start with the introduction. And what wakes up the supermassive black holes in galaxies was the central question, basically, when I applied for this PhD. But before that, let's talk about the galaxies. So what are galaxies? We know nowadays we live in a universe full of galaxies, and usually you can find basic definition from Wikipedia. So galaxies are collections of stars, dust, gas, and dark matter. Let's not talk about dark matter right now. But the first thing that astronomers started doing it more than 100 years ago with galaxies was looking at them. So what you can see here on the right-hand side was what we call nowadays the Hubble sequence, the morphological sequence. So once you take images of these galaxies, at the time 100 years ago, Hubble was calling them still nebula because they were classified as external galaxies yet. He was just classifying them by their look appearance. So you will say this is kind of a spheroidal or elliptical galaxy. Those other one on the right side of this sequence resemble spirals just because you see their beautiful spiral arms that are wrapping around their center. Then you have some other ones that you can call irregulars because they didn't have any regular shape. or you will have some of these other spirals with a bar in their center, so simply you can call them barrel spirals. But the fortune of this scheme was not that, as Hubble proposed, was a sequence of evolution, but is that with 100 years of studies, we found out that actually this morphology correlates with numerous properties of galaxies. For example, it correlates with the total mass or stellar mass of galaxies itself. So you have that the more massive galaxies are usually ellipticals, while the lighter ones are spirals with their star formation activity. So simply how frequently they form new stars, or which is connected to their gas contents that we know are translated from gas to stars. So usually you see that you have larger star formation rates in those spiral galaxies compared to the elliptical, or the environment where these galaxies live. And this is not all, because what also we discovered is that all of these massive galaxies, or at least almost all of them, have in their center a supermassive black hole. By definition, is black hole is something dark. This is just an illustration from Interstellar, so I don't think that it's actually real, but gives a nice idea what is a black hole. But although those huge black holes span wide ranges in masses, they're indeed dark, and actually you can't really observe them. The black hole is in the center here of this illustration, or as nowadays we have a couple of examples thanks to the HT collaboration here obtained through interferometry. What you observe is the matter falling in. So now I will give you a bit of more details in the next slide, but what you have to try to imagine here is that the black hole is kind of a point source at the center of this picture, of this image here. And what you can only observe is the matter is falling in, and while it's falling in, is emitting light and electromagnetic radiation that you can observe. So this is not usually the black hole when people think of the supermassive black hole, but you have to think of the dark center that you can take in these pictures. But then let's try to understand what is, for me, a supermassive black hole and what I try to do with this. So for me, actually, what I like to talk is the active phase of the black hole, so the AGN, Active Galactic Nuclei. Because when we have this accretion of matter that is falling in and is emitting radiation, what you're doing is actually converting this gas that is falling in into gravitational, where the gravitational energy is released, and you have emission of electromagnetic radiation across all wavelengths that you can imagine, and this AGN, active galactic nuclei, becomes extremely bright, and you can observe it. In some cases, some extreme cases, this AGN is actually outshining the galaxy that is hosting the central structure. Nowadays, we try to describe the black hole with this sketch here, and this AGN phenomena is actually, this AGN is composed of different phenomena that I'll try to explain if the movie starts. Yes, the movie is lagging a bit. Yeah, okay, I'm sorry that the movie is not playing. It was much nicer than this, but so again, let's try to imagine that in the center you have the black hole. We'll try to imagine there, and this structure is surrounded by an accretion disk. So now, as I say, I'm sorry that the video is not playing, but basically you will have matter that is spiraling around the central black hole, and it's thanks to the gravitational force falling to the black hole. And while it's falling, it's emitting radiation, and the radiation is emitted through different components. You have this corona structure here that usually glows in the X-ray, and so if you do X-ray observations, you can observe the corona of the AGN, for example. Or also you can have the formation of radio jets. So in this case, thanks to synchrotron emission, you can have these elongated jet structures that come out of galaxies and extend well beyond the galaxy structure that you can observe with the radio observations. Or you have this dusty torus. So surrounding the whole accretion disk here on a large scale, you have a whole torus formed of dust that actually is absorbing the radiation coming from the disk here and radiating it, for example, in the infrared. So you can observe this phenomena in the mid-infrared with or infrared observations. The rates of accretion vary a lot. You have some very steady supermassive black hole. They have a very low accretion rate in terms of solar masses per year, while you have others that are extremely powerful that are accreting several solar masses per year or slightly less. And the energy release is actually a release for what we believe across all wavelengths, although you don't observe them usually simultaneously in all wavelengths. Why do we care? It's not just because I did the PhD that we care, I think. I think there are several reasons why we care. The first one is that when you look at the galaxy represented earlier and their morphological sequence and the supermassive black holes, there are several hints of a co-evolution. So the two things we think that evolve together and probably also form together back in time. To mention a few, I like always to mention the first two that were observed, the relation, for example, between the mass of the black hole and the mass of the host galaxy is extremely tight. Or you can have also the different variation where you have this sigma bulge is basically the velocity of stars in the bulge of the galaxy you're observing. So the velocity of the stars in the central region of the galaxy. And this is quite tight across a wide range of masses and across a wide range of masses also the black hole on the y-axis and masses of the galaxy on the x-axis, or the velocity of the stars there. And this is indeed an hint that probably the two things grow together. And indeed, we also observe what we call feedback mechanism. So this huge amount of energy that is released by the AGN actually influences the galaxy itself. So what happens is that, for example, I showed you a jet. The jet interacts with the structure of the galaxy, and, for example, can stop the formation of new stars in the galaxy per se. So you don't have just a mechanism for which the galaxy is fueling gas into the supermassive black hole, but also this supermassive black hole, once is active, emits a jet, and the jet influences the structure of the galaxy itself, closing this feedback loop. And the problem is that we still don't know what is the physical actually mechanism, because it's nice to explain this with this sketch and illustration, but actually when we go in concrete, we don't have, again, a physical mechanism that explains this coevolution. And this is what we usually call the fueling problem. This has been a long-standing question for the last 30, 40 years in the field. And the problem is that you need to connect the scale structure of a galaxy with the scale structure of the supermassive black hole in the center. To give you some numbers, you need to move the gas from outside the galaxy, because maybe the galaxy doesn't have a lot of gas. So you have, again, looking at this illustration, you need to bring the gas from the center, from the outside of the galaxy towards the center. So you need an inflow of gas, so moving them from 50 kpc towards a central region, let's say the last kiloparsec, so kpc, and then to the surrounding of the black hole where you go down to scales of few tenths of parsecs, or in the very last bit into fractions of parsec. You just don't need, it's not just that you need to bring the gas, you also need to cause a loss in the angular momentum in order to efficiently then accrete the matter. What can we do? So we have been proposing several mechanisms, but nowadays we basically try to send them with the two main categories: external mechanisms that are usually referred as galaxy mergers. So I will give a brief intro soon, or internal processes. So for example, earlier I showed that some of these spiral galaxies have a bar in the center, and the bar you have to think it as a conveyor belt. So it's a way that you can bring the gas from the spiral arms toward the center on this conveyor belt. But the main topic of my PhD were galaxy mergers, and galaxy mergers seems the #1 suspect for investigating this problem and trying to understand this connection. First of all, because it's beautiful to look at galaxy mergers, so usually astronomers spend a lot of time in imaging these kind of galaxies and trying to study them. And what you can see here indeed is a sequence of different observations of two galaxies that interact with each other and will form a new, more massive galaxy. And this is the key aspect of the galaxy mergers as a mechanism for fueling the AGN, because it is a way to increase the mass of the galaxy, and is a way to increase also the mass of your supermassive black hole following the same rate. So you will try to explain in this way the correlation between the black hole mass and the mass of the galaxy, and will cause also morphological transformation. So you will go from spiral galaxies like this in the picture number 4 to the elliptical galaxy that you will see at the end of the Hubble sequence. So this seems perfect, and indeed they are an efficient way to funnel the gas toward the center, and also to create extra gas supply. So for example, if you're finishing your gas, you just merge with another galaxy and you basically are doubling your amount of gas that you can give to your black hole and cause an angular momentum. loss. And of course, this has been tried and tested with different simulations, and all agree that actually mergers are one of the main ways for the accretion of the supermassive black holes. So if you go back to the fueling mechanism, you will have basically this scheme. The top one that follows mergers. So you have subsequent events of two or more galaxies that merge, interact together, and will basically give birth to this powerful emission of the AGN, what sometimes we call quasars, and eventually produce the elliptical galaxies that you observe nowadays in the local universe. Or you can proceed in the internal way. So once you form the spiral galaxy, let's imagine it's a spiral galaxy, this one has a small supermassive black hole compared to the case of the ellipticals, is steadily accreting some gas towards the bar, for example, and there's a low luminosity AGN, and then you have the formation of galaxies like the Milky Way in the now in the local universe again. So since we solved the problem, this explains everything fine. You go to the literature, I will actually, like some of you later will try, you just start basically merger AGN connection ADS on the archive, and you find the tons of works. Half says yes, half says no, there is no observational correlation between the two. And this is really puzzling. I think I just stopped at the first 10 that I found, like five that say yes, mergers trigger AGN, and 5 says no, mergers are not responsible for the fuel of this supermassive black hole. Why this problem? The problem is that there are so many observational biases going on here. The first one that you can think is the different way of you select this AGN. As I mentioned at the beginning, you, for example, can select AGN using the X-ray, or you can select them using mid-infrared observations. If you use mid-infrared observation, for example, you're actually selecting just the dust obscured AGN. So the case of the AGN where you're looking through the dusty torus, and so you are looking at the, let's say, the edge-on case of the accretion disk of the supermassive black hole. And you are not looking at the ones that, for example, you could detect in the X-ray looking at the corona component of the AGN. And those usually inhabit different types of galaxies, and so is a bias that you will just basically have reproduced in your own analysis. Another problem is the way you define mergers, because if we go back at the image and you have the different stages, at which point you start saying, okay, this is a merger, this is not a merger, it's still an individual galaxy. This can turn more into also a philosophical question, but also the way you identify them in the images. And also let me mention that there were problems with the different redshifts, luminosities, and the samples, because until like a few years ago, the samples were extremely small, especially using the previous generation of telescope like Hubble that had a small field of view. So what we tried to do, yes, in my PhD was addressing these points, trying to solve the sum of the biases I mentioned. So we use a multi-wavelength approach. So this way we try to eliminate the component of, okay, you're just selecting AGNs in the X-ray, or you just in the mid-infrared, or just in the optical, whatever. We try to cover the whole spectrum. Then we use the large surveys to try to cancel out the problem with the small sample. And what we did is try to have a full galaxy and AGN characterization, and going into what I will describe later in methods as the spectral energy decomposition fitting technique. And then using machine learning, not before it was famous, I would say before the launch of ChatGPT. So we're still doing a hard way this to try to be reproducible when you do the classification of the images in the optical. So I will think now is time to move to the methodology. Hope it's mostly clear what was the problem and the setting up of the stage for this investigation. And let's start from the multi-wavelength aspect of my work. So what we believe, especially strongly, my first supervisor, a strong believer in this, is that in 21st century astronomy, we should have this multi-wavelength approach. Thankfully, over the years, we have launched many facilities, many observatories, also ground-based, that observe the electromagnetic spectrum from X-ray, actually even gamma ray, all the way to the radio. And we should now make use of this information that we have in the databases. Probably, I sometimes say, probably there is no need of new observations. There is full of data that you could use going online. And what we tried to do was collecting data from X-ray observatories like Chandra, Eurosita, XMM Newtons, then move to the visible with the first ground-based facilities like the Subaru HSC camera, BST, Vista going to our infrared, and then also moving towards the space observatories like HST, Hubble, sorry, and Euclid and James Webb once they were launched, all the way to Herschel, that probably is a telescope that not a lot of people heard of in the sub-millimeter regime. And this gives you the opportunity to fully characterize your galaxies, not just looking at single aspects. And indeed, as I mentioned, what we did was SED fitting, so spectral energy decomposition fitting, because once you collect all this data across the whole wavelength range that you can imagine, what you can try to do is try to fit the different components of galaxy and black holes. We use this software called Seagull. I'm sorry that it's not really showing a lot, the logo on the upper right, where we use the component of stars. Of course, galaxies are made of stars, of dust, and AGN, where we included an X-ray module. And well, Skirter is just the name of the template if you're curious to and want to reproduce our results. And this gives you then not just the full, for example, mass of a galaxy, but this code is able to disentangle how much light is coming from the AGN, for example, of course, making some assumptions. So you have always to bear in mind that you are making strong assumptions, but also which part is coming from the galaxy, for example. And so on top of star formation rates, stellar mass, you can obtain these two properties that for my work were fundamental. The luminosity of the AGN, the total luminosity, not just the part, for example, you see in the infrared, and the AGN fraction. What is the AGN fraction? If we try to look at this spectra here, it's basically counting how much light is coming from the AGN over the total light of the system AGN plus galaxy. So we did it into the range 3 to 30 microns, so it's roughly this this green band here. You see the different line colors are different components, dust, AGN, and stellar, and you just basically calculate the fractional contribution of the AGN over the total light emitted of the galaxy in that wavelength regime. After this, what we did is indeed identify the AGN. So we had this wealth of data. So we use X-ray detections, in some cases the optical spectroscopy, that probably I didn't mention is another way to detect AGN, mid-infrared colors, the SED fitting I mentioned earlier, and there is also another technique that is called image decomposition that we use just in the latest year when we had too many galaxies to do the SED fitting in a fast way and efficient way. And I will just give you details later because concerns really the only chapter of my thesis. Then once you have the AGN, you characterize your galaxies. What do you miss? You miss the morphological classification. And this is where we started heavily using machine learning. And this basically comes naturally. As Marco said, during my master, I worked with a galaxy cluster nearby, Hydra 1 or dwarf galaxies. And there I had about 300 galaxies roughly confirmed that would belong to the cluster. But in total, there were like 1,000 galaxies in the image that I was looking at. I could still look at them eye by eye, one by one, and classify them basically with my supervisor at the time. Here we are talking about millions of galaxies. This is something you can't really do anymore. And so machine learning is the only way you can actually perform this, also in a reproducible way, because I know that my algorithm, if I give the same image, will give me always the same output, because in the end, what it's doing is doing some mathematical operations and will give me a number that is always the same at the end. So what we did is generating some mock images, because one of the problems I mentioned is that it's hard to define what is a merger and what is not a merger. So we started from simulations, these two that I'm mentioning here, Illustrious TNG and Horizon AGN. And from these two simulations, since those are you know the ground truth in that case, you know which galaxies are going to merge with each other and which are not going to merge with each other. We make them as realistic as possible, and then we trained our models, which were simple convolutional neural networks, to give a label in the images as mergers or non-mergers, very, very basic at this stage. And then we test on real data. This was, of course, the challenge. I always like this meme because something is mock images. You can work as much as you want to make them realistic. Some is the real data. Because the problem here, of course, as you see this small meme, is that something really looks like mergers, but is not in reality. For example, can be a galaxy and a foreground galaxy, and you are confusing your algorithm. But then you have to deal with that. So you need to estimate what is the performance of your method, and then do some prediction. And then at the end, what we did was combining several models tested on the different simulations to try to improve the overall performance and obtaining something that we can trust and we believe is on average correct in the classification. This was for mergers. For the other part, we looked at the bars as the other possible way to fuel the AGN. These are beautiful examples, but many more cases it's harder than this. The bar is much smaller, or the galaxy is much farther away. That's the bar is very confusing to detect. And in this case, we use a bit more fancier approach. So we use as a training sample Galaxy Zoo. I don't know if you ever heard of a Galaxy Zoo, if you ever played online classifying galaxies and images. And we use that one for fine-tune. So in this case, we have millions of classifications from like humans and citizen science projects. And we trained a model called the ZooBot that is much more complicated than a simple convolutional neural network. But nowadays it's basically one line of code, thanks also to the AI tools to just import a line of code. And in this case, it's a Bayesian approach, so it's going to give you some Bayesian and probability as output and not just a classification on a single label. And all of this was possible thanks to a master student I supervised in Groningen, which made really an amazing work. And also, we tried maybe to quickly touch on it. We tried to classify bars also according to how long they are, how prominent they are, because you can divide them as strong and weak bars according to basically their length compared to the whole galaxy. So this is a bit of wrap up of the methods we used. So we can now move on to the results I would like to discuss. Let's start for the result in the first half of my PhD. So in the local universe, let's say that. And what we did. First, galaxy mergers, and then the role of galaxy bars. So quickly, for the data used in this work, I used the region called the Gamma 09. This is about a 60 square degrees field observed with the Subaru HSC telescope, and we selected relatively massive galaxies, where massive I mean 10 to the 10 solar masses, up to redshift 0.7. And use these AGN selections, so X-ray, making red colors, acid fitting, and we are about 32,000 galaxies in this sample. As you can see, if you compare the moon, the field is quite large, although it's a bit cut in the slide. I'm sorry for that. First experiment, AGN frequency in mergers and non-mergers. So you have your catalog. You have galaxies that are classified as mergers and non-mergers, and galaxies that basically you label as, okay, they contain an AGN or they are inactive, they don't contain an AGN. The first question we want to try to answer was, okay, can mergers trigger AGN? This is something already done in the literature, so it was nothing new. And the idea is that if you find a higher frequency of AGN in mergers compared to the non-mergers, then this is a huge hint towards mergers are connected to the AGN and trigger the AGN, and one of the possible mechanisms. So basically, you put together is a really basic fraction. If you wanna do it, it's basically you count how many galaxies are classified as mergers and host an AGN over the total number of mergers, for example, and this is going to give you the AGN frequency in mergers, and you do the same thing for the non-mergers. What did we observe here? So this plot, start looking at the top panel, basically is showing in different beams of redshift and different selection. The colors indicate different selections of AGN. What is the frequency, AGN frequency in mergers, the filled symbols, compared to non-mergers, the empty ones. The first thing you notice that it doesn't matter basically the way you select AGN or the redshift beam you're looking at, but there are always larger fractions of AGN in the mergers compared to non-mergers. So what usually people does is creating basically the ratio of these two quantities, so the fraction in mergers and the non-mergers, and calculate an AGN excess. And this is what is shown here in the bottom panel. And our results were basically comparable to this part of the literature that were confirming then that there was this higher frequency of AGN in mergers compared to non-mergers for the same AGN selections. And we were happy. This was a factor between 1.5 and 3, so it means that you have 1.5, 3 times more AGN in mergers compared to non-mergers. And in this case, we were also controlling for masses. So the galaxies we were comparing had the same stellar mass. To be sure, we were looking at the same, we're comparing basically the same galaxies. But this was a bit old style of doing things. It's just looking basically at the universe as black and white. You say, okay, things are just mergers on mergers or AGN on AGN. So what we try to do is adding the flavor of the grayscale here. Since we have access to this quantity AGN fraction, let's see what happens as a function of the AGN fraction. So doing a bit more complicated stuff. And so the idea is that now on the x-axis, you have the AGN fraction of the individual galaxies, the one we estimated in the range between 3 and 30 micron in the green band, if you recall, and calculate the merger fraction in beams that were variable size of this AGN fraction for the different, again, colors, the different AGN selections. What we notice is that basically there is almost no relation between the merger fraction and the AGN fraction in the first part up to 0.8 AGN fraction. For all 3 types of AGNs, you have a flat merger fraction saying, okay, basically it's constant, it is roughly the merger fraction of the universe, so probably there is no connection. But when you go in this regime, and I'm sorry that the color scheme is not very visible here, where you are looking at the most dominant AGN, so the AGN basically accounts for almost all the light of the total galaxy plus AGN systems, the merger fractions in all 3 cases goes up to 80%, almost 100%. So the idea we had is like, actually, this is a hint to explain the different results in the literature. Because here we see that for the most dominant AGN, mergers clearly play a role. You see that most of these galaxies are actually classified as mergers, while in this other side, probably the secular processes are playing a larger role compared to the mergers. So what we did indeed is triggered the master project. We did is say, okay, let's try to see if bars here are responsible to explain this part of the diagram to these other roughly 60, 70% of AGN galaxies, and let's see what happens there. And that's exactly what we did. So now on the y-axis, you have the bar fraction, and the x-axis is the same AGN fraction in the same range. The difference in the columns here is that we divide the galaxies, as I said, in strong bars, weak bars, and all bars together, putting together the 2 samples. The lines is just to get is a fit to our previous relation, so it's just to get your eye to what was happening earlier. But basically, what we notice is that the bar fraction, doesn't matter the strength of the bar, is again kind of constant with the AGN fraction, but this time it drops down to 0 or stays kind of with very large uncertainties. Basically says the same value also for the most dominant AGN. So you don't see what we observed actually for mergers, so the huge increase in merger fraction. And then we try to do this also with the other continuous parameter we have from the SAD fitting, the luminosity of the AGN, that here was actually the luminosity of the accretion disk as a proxy of it. And again, you basically observe the same thing. While for mergers, the line, you see a sharp increase after a certain threshold value. So for the brightest AGN in our sample, for the bar case, for the bar, you just see actually it drops down to almost 0. And this is actually the discrepancies that we were looking for. It was a really nice confirmation. And if I have to summarize what we found then at local universe, is basically this scheme on the right-hand side, where basically we confirm that both mechanisms are responsible for the AGN triggering, with their exact role that it's probably AGN luminosity and fraction dependent, so that mergers can explain the most luminous AGN in the universe, while bars, as well as other mechanisms that we didn't have time to investigate, will be probably the ones that can explain the low luminosity AGN regime. So now we can move to the second part of my talk. Sorry, just taking a sip of water. I was very lucky, I have to say. I always like to say this anecdotal story. When I did my PhD interview, basically it was very fun because they were mentioning, yeah, you're going to use the James Webb images, Euclid images, and so on, but like I didn't believe it. because as all these facilities were like always delayed, I'm like, yeah, sure, it's gonna be launched in 2030 and I'm not gonna work in it. But I was lucky. I was extremely lucky that actually Euclid was not that much delayed and James Webb was finally launched. So I actually had the chance of working with them. And the Euclid I also was very, very lucky because I was able to go to the launch of Euclid in 2023. So it was an amazing experience. And what we did is basically, let's try to redo the same experiments, but now you can look at higher redshifts. Starting with the James Webb, we use the Cosmos Webb field to give you, again, an idea, is this orange area, and this is the moon for scale. So if you try to go how small was the moon in the previous image, you see how how much smaller the area in this case, but James Webb is much more powerful and can go deeper. So in this case, I could extend my sample to lower mass galaxies, going down to the 10 to the 9. I can go to higher redshifts and observe up to redshift 2, so where galaxies were much younger. And there was also what is called the peak of the star formation rate activity in galaxies. So we still end up with 10,000 galaxies, so 1/3 of earlier, but still a statistical relevant sample, and try to use the same AGN selections. Same experiment, AGN frequency in mergers and non-mergers, but with this data. What do we find? Well, basically we found the same kind of results with different numerical results, but qualitatively the same. So again, if you look at the top panel here, you see that in all cases, you see there is a larger AGN frequency in mergers compared to the non-mergers, and when you calculate the ratio, in most cases this is compatible with an excess of a factor 1.2, 2.5, so mildly lower than earlier, but still comparable, especially if you consider 1 sigma uncertainties here, and that you are looking also at different redshift range. Then the other relation, we try to match what we also found in the literature in the same field, so using the same Hubble, the same field, but the Hubble images. So again, merger fraction as a function of AGN luminosity. Again, for all 3 cases here, you see an increase. This time, you don't see actually a flat trend in the merger fraction with the AGN luminosity and then a sharp rise. You see a more constant, actually, increase of the merger fraction in the samples, and we were mostly in agreement with the previous studies, but starting getting to smaller and smaller uncertainties, especially if you come to, for example, those 2 points had literally 10 galaxies in their sample. And again, this was a clear trend. We try to explain this, saying that merger efficiency in fueling AGN activity increases with the higher luminosity of the AGN. Or, I always like to say the reverse, that, for example, the internal processes like a bar are not an efficient way to fuel such a powerful emission from the AGN, because simply those structures are not capable of bringing enough gas toward the supermassive black hole. So in the most extreme cases, you need a merger because you need much more gas onto the supermassive black hole. And that's great, but again, there were a lot of uncertainties, and luckily there was Euclid that is literally a game changer for this type of studies, because there were very limited samples of mergers and AGN at redshift larger than 1. So Hubble, the points I was showing in the previous line, was about 800,000 mergers when you consider all the candles field and this reference work. We're talking about 4,000 roughly galaxies in the same mass range. JWST in my work in previous chapter, talking about 10,000 or 13,000 galaxies, of which less than 2,500 mergers. But Euclid, you have a very high spatial resolution, so you can still detect the merger features at high redshift. You have a much larger area. So the data used was the QUIP data release 1, was about 62 square degrees, so comparable to the previous observation from ground-based facilities, and is an excellent way to study morphology of galaxy. So we did it, and we had 100,000 mergers. So this is not just 100,000 galaxies, it's 100,000 mergers. Galaxies were more than 1 million just in this first release of data sets. And yeah, of course, here you see some of the examples that my CNN classified, I would say correctly, as a merger, but we can discuss it, and some of the cases where the galaxies were labeled as non-mergers. But this brings you in a completely different type of statistical regime for this type of investigation. So a bit more details. The sample is mostly massive objects, around 10 to the 10th solar masses, and 62 square degrees, as I mentioned. And we used also the image decomposition, because once you have 1 million galaxies, and there was a hard pressure to publish with the first data release all the papers in a coordinated way, you can't just go and do the SED fitting for all these millions of galaxies. It will take you basically months and months. So what we did is try to develop another machine learning algorithm to divide the galaxy light into a central PSF, which represents the AGN, so the supermassive black hole that is actively accreting, and the host galaxy. This was already done in the past, but usually was done with softwares that were fitting the light of a galaxy rather than using machine learning. But machine learning for those things is just faster. And actually, we had an improvement in the overall performance. So this model, what does is calculating this PSF fraction, and again, was trained on a sample of all, this time, real objects. So we had the real Euclid images where we injected a central PSF of a fraction that, of course, we knew how much we were injecting, and trained this model to predict this PSF contribution. And so from now on, I will talk about the PSF fraction and the luminosity of the PSF, and not really AGN fraction and the AGN luminosity. They're not exactly the same thing. We are aware of it, but let's imagine they are proxies for it. And what did we find? So same experiment, as always, AGN frequency. Again, this was just a nice confirmation. It's the first type of exercise that you do when you're doing these studies. Okay, let's see that if I can confirm what we found in the previous 3 years and with the other data. Yes, we did. This time we adjusted more AGN selection. So what I'm mentioning here as DAISY is optical spectroscopy. I'm sorry that I forgot to introduce it earlier on. Again, a factor of 1.54 according to the AGN selection you're using. But this is great because, again, we are confirming with a much higher statistical power the mergers triggering of AGN. And indeed, on top of the agreement with the previous studies, I really want you to focus on basically on the uncertainties that I try to show here, but they're basically invisible in most cases. When you propagate for the excess, of course, some of them show it, but many others actually not even when you propagate, but as well, that there are actually here uncertainties. And when we go then to the merger fraction versus PSF luminosity, when I produced this, the first time was a shock for me because I was plotting the normal uncertainty and basically was hidden below the thickness of the line. And then what I started doing is plotting the 3 sigma range of uncertainties here, but we observe the same exact trend. So let's try not to look at this gray line here, if they can confuse you, but if you look at the 2 lines that are the 2 different redshift beams we divided, again, you see an increasing merger fractions, an increasing fraction of galaxies classified as merger with an increasing PSF luminosity. And this is exactly what we were observing earlier with the bolometric luminosity of DGN, and is leading us to the same conclusion. So when I look at the brightest point sources or the brightest AGN, mergers are dominant in that sense. They are the number one morphological type triggering this activity. Some tries also to say, well, but with these statistical uncertainties, since those you divide in 2 redshift beams here, you see also redshift evolution in the lines, so there is also an effect of with the evolving universe. But thanks to this large sample, we could do something that we never did before. So I kind of lied so far. I use, as I say, the machine learning and say, okay, this is reproducible, it's amazing, it's just the label to the galaxy, perfect. Machine learning is not perfect. Of course, it's going to say some galaxies that they are mergers, while they're not, and some others, they are isolated galaxies, well, they are not, they are mergers. The problem was, okay, how can we account for this systematic? How can we account for the problem that the model is not perfect? And we came up with a Monte Carlo simulation. And we could do this because we had many, many galaxies. And so statistically, we could be able to adopt some more sophisticated methods, I would say. And so we ran this simulation. And what we did is relabeling galaxies according to some performance. If you like the details, I'm happy to talk about it. And giving some weights to these samples that we were regenerating with the Monte Carlo simulation, and then estimate our systematics. So the uncertainties that you will have according to the network imperfections. And now I'm showing basically the combination of the two uncertainties, so the systematics plus the statistical uncertainty that were in the previous plot, and you see that they are much larger, simply because the network performance is here lead you. It is not anymore a problem of the statistics of objects that you had. But what we were happy is that the overall trend still holds. Even with these large systematics, you still see the same trend. I will say probably here, once you see this, it's much harder claiming there is a redshift evolution. But overall, we were really, really happy. So I'll move to the last session, to the last section of this talk, since also time is running out, to draw some discussion and conclusions. So trying to put all pieces together of these 4 years of PhD was really, really nice, I have to say, and to defend, because we came up with this idea. Of course, it is not that it's just our idea, it's something in the world literature, half of the literature was spending already their time. The idea is that if you imagine galaxy evolution here as a timeline on top, and then you look at this plot where you have the merger fraction as a function of the luminosity of your AGN, where do you start? Well, you start with maybe an isolated galaxy, spiral. You can have a bar, not have a bar. Maybe you're also inactive, or anyway, you have a low luminosity AGN, and probably you are in this part of the region. So there is a very low chance that you're actually in mergers, but most chances are that you are in a normal evolving spiral galaxy, for example. Then you start interacting with other galaxies, and then these basically, as the interactions goes on and you have more and more gas going towards the center, you increase your AGN luminosity. And so moving in this direction, the x-axis, you actually have a larger fraction of galaxies you would classify as mergers, because you see some features, so you see a companion, until to the point where you are in the full post-merger phase. So in the case where basically you don't see anymore your companion, but you see a single disturbed galaxy, but with the extremely powerful AGN. And so basically you arrive to the point where almost all those galaxies with extreme bright AGN are classified as mergers by the models. And then what happens? Well, it happens as the gravity goes on and your galaxy basically settles down and form the elliptical galaxy. And those usually go back to have low accretion rates and low AGN luminosity and go back in our diagram here. And so, like, if I have to conclude with that takeaway, usually I would say that AGN fueling is not governed by a single universal mechanism, but it's rather a combination of internal processes and external processes, where the internal one moderate the low intermediate accretion to supermassive black holes, while the brightest AGN actually are the trigger of the, are mostly triggered by major mergers. And I think I don't have any more time, right? So I will just leave the future ongoing prospects and go to the, all this, we skip it up. Okay, and leave you my summary and take your questions. Thank you.
Thank you, Antonio. Is there any questions?
Please, congratulations for this interesting talk. But I have some problem. I have not fully understood your definition of merger, in the sense that we know that merger can occur with a variety of galaxies. There have been different mergers with completely different characteristics concerning the mass of the structure. So when you talk about merger, you are talking about really one-to-one merger, a big galaxy that.
Yes, I can clarify this. Thanks a lot for the question. As I mentioned, well, maybe it's easier if I go faster from here. Yeah, it's very hard to give a single definition of merger, because as you mentioned, to some extent, basically everything is a merger. Like if you say, okay, even just size of the Milky Way, you have the small satellite, the larger and small Magellanic Cloud, you say, well, we're going to measure them, this is a measure. Totally true. But the problem is sometimes, to some extent, is philosophical where you draw the line. In my case, we basically talk about major mergers. So cases where the galaxies are in a mass ratio between 1 and 1 to 4. So up to the minor galaxies being 25% of the major galaxy. Because, well, first of all, because it's easier to detect them. So let's be honest, it's much easier because you see the second galaxy. So cases like this one, or you have a major one and the second is still prominent, you can see it. So it's easier to pick them up for the machine learning algorithm. And the second case also because if you start looking at the minor accretion events, as you want to call them, or minor mergers, as some other people call them, then basically you can say merger is the cause of everything. Because everything will be a merger, everything is accreting some dust, some stuff from external sources, and then in a merger. The other problem is the time window that you use. So where do you draw the line? Like, is this a merger or those are two isolated galaxies? This is also another problem. Because when I go to the simulation, it's easy. I know when they are going to merge. So I can take the image exactly when they are going to merging, or slightly before and slightly after it. In the real universe, it's hard to say, okay, this is going to be a merger event in a giga year or in 100 mega year. And then you make some assumptions. And
I think you are trying to correlate the properties of your agenda with the merger, or speed that the merger trigger the fueling of the agenda. So in that case, for instance, I'm not an expert in this. Sure. This case is not supporting that scenario for the simple reason that the two galaxies are not yet merged.
Yeah, so we try to do that. So what we started trying to do is adding the causal link between the things. So when you have the pre-merger phase, you should not see the excess. And after, so for example, here or here, you will see the excess. We try to do it. The problem here, and we have a paper on it with a great master student. The problem is that the performance of the algorithm, when you want to go in this level of details in splitting mergers, is much lower. So you will have many more misclassifications. And so if you take into account that basically the correct classifications are just 66%, the results are not very robust. So they are going in the direction we believe it. So in this phase, there is no difference with an isolated galaxy. But then like you really need to trust your method, and I would say it's not so trustworthy.
Could you say something more about these data layers, the bar that move up from outside toward the center? So, what is the physical mechanism for which the bar is a preferential room?
Yes, this is a
Gravity conditions.
great question. Is basically the way gravity acts in the central region, in the bar that is formed. How can I explain it? So it is, so the way that gravity will then affect stars and gas there is that they will not move anymore in an ordered way. So if you imagine the spiral arcs, stars and gas here, they are moved in an ordered way, following basically the rotation of the galaxy. While the kinematic of a bar is much more chaotic. And while you have this chaotic movement that again goes toward the center of the potential, that is the black hole in the center, you are causing the angular momentum loss of the gas. So it is an efficient way to basically cause the angular momentum loss, because also a normal spiral galaxy will actually have this inward movement of gas and stars toward the center just because of gravity. But the bar had an easier way to cause the angular momentum loss, basically. Don't know. Sorry, I really didn't.
think there are also some things associated with the fact that the bar can induce a resonance. And the resonance can trigger the channeling of gas and also in the center, as well as to change the mechanism for stellar migration, enhancing all this.
Yes,
The direction of the
exactly.
other one.
Yeah, indeed. Yes, exactly. The resonance also helps in this sense.
So very nice talk. So a few years ago, there was a somewhat similar study, but not looking at star formation. With a few papers, they looked at 3 million or something, 5 million galaxies from SDSS, and they looked at so they would fit mergers, and when there were two nearby galaxies, they would fit a bulge plus disk to each. And they looked at the separation in terms of effective radii, and then of course they had spectra because it was SDSS. But they were then plotting separation versus star formation rates. Have you looked at that, like separation?
Like,
coming back to the question,
yeah.
What is a merger, and see when it actually, there is some kind of internal effect.
So I didn't, but the same group actually did it also with AGN. I know which group you're referring to for that work. They was the group led by Sarah Elvison, actually, yeah. And they actually indeed did the same with the AGN contribution with SDSS. And indeed, you see actually in their case that as they were getting closer to the galaxies, you have an increase in the AGN frequency in this screen merger. So if you just basically were plotting the AGN frequency plot, so this one, so imagine of doing this for different separations, yeah, you were going that the AGN frequency was, or the excess, if you want to look at the excess was going up when you go closer to galaxies to each other. The problem that of that work that we appreciated and they pointed out is that, of course, you are limited to pairs in that case. So then you're excluding the post-merger phase where you should see the largest excess. And they tried to follow up it, and they did it recently. There's, I think, Robert Bickley work in the last couple of years, where they focus on post-mergers, so taking just the post-mergers, and indeed they see that actually the excess here will be out of the scale, will be like a factor of 10, if I remember correctly. So in that case, will be the largest, confirming basically what we were saying in the sequence.
And you have the post-mergers because you did machine learning and a training set said this mess is actually a merger.
Yeah.
Thanks, that's beautiful. I have a million questions. We'll talk about that
Tonight.
after the but I don't know, maybe it's related to what was I mean, since I've been in discussions how do you find a merger, there are these dual AGMs, right?
Yes.
They are kind of a smoking gun.
Exactly. Yeah.
What do they say about that?
Yeah, that's exactly what we are working on actually in Euclid. And we are full because the dual AGN is what we like to see. Because the dual AGN, as you say, is a smoking gun because you have exactly the two black holes are going to merge. And this is the perfect case. There is a caveat that during interaction, it could be that also, at least from simulations point of view, from a numerical point of view, many cases show that only one of the two black holes is triggered and not the other one.
And then that's the other thing.
And that's the problem, because in that case, then the dual AGN will be just a particular case, the most gas-rich one, where you have enough gas for both of them. But yeah, we were working on that actually in Euclid, and we found a confirmation of it. That you have then the dual AGN, most of them in the, of course, in the merger source of galaxies, in the post-merger phase, as you would like to see.
I do have time for a technical question. If you go back to the slide where you showed the machine learning, the things,
the pipeline,
along the images, do you believe that? I mean, I guess you look at your data, one with the mergers and the isolation. No, the one with the many cutouts. Yeah. I don't know.
Okay.
Mergers and both that ones. So this is machine learning, I suppose.
Yes.
Yeah. Visually, can you tell, I mean, you have the feeling that you have higher probability of fake mergings, or contrary, higher probability of
No, but I can answer this not as a feeling, as a statistic. That's an answer going to be also clear. That's what led our Monte Carlo simulation.
yeah.
Like I have the numbers. There are more. So it depends with the output of this CNN. So the input of the CNN will be the cutout of an image of a galaxy, does its math and gives you a number. In my case, numbers between 0 and 1. 1 will be I'm 100% convinced it's a merger. 0, I'm 0% is convinced it's a merger, or 100% a non-merger. No, the problem is the threshold. If you want to give the binary, and unfortunately I didn't have time, but that's where we're trying to give the next step is like try to avoid that the threshold makes your difference. You know, because if I say I take the threshold 0.5, I will have a certain performance and a certain number of misclassifications here and here. In this case of study, since we had these statistics, what we cared was purity of the sample of mergers. Because in the universe, there are many more non-mergers, at least major mergers. Sorry if I use the word mergers as major merger. So in the universe, there are many more normal galaxies, or like minor mergers in many cases, than major mergers, okay? So what we wanted was that, okay, I want to maximize the purity of this sample. And if I have more contaminants in this sample, I kind of don't care because there are so many more non-mergers that just is not gonna be a problem. And so doing this way and the way I set up the threshold, the answer is no, there are many more contaminants here, actually, as a relative sample. Then if you go in the actual numbers, since here there are 900,000 roughly non-mergers, and if there is a contamination of 15%, there is still many more non-mergers than mergers. And yeah, but indeed that's also why I go to the Monte Carlo simulation. Yes, okay. If you try to look at the orange one, here the systematic is much larger than here. And this is actually because we investigated this, because at the beginning it's like, why is actually there is this trend in both cases of the systematics going down? And it's because here there are many, like since the majority of these galaxies are mergers, the contamination here was lower. So the Monte Carlo, the sample, there was lower contamination per se, compared to here where there is much more contamination.
There are more questions or discussions, we can keep going to the coffee. So we thank Antonio again.
Two updates. We have a seminar next week, not programs. Collaborators such as Kazakhstan. It's going to be a talk, I suppose, always still Thursday afternoon. And as you have seen, John Blakeslee sitting from one lab to some is visiting us from the next one. And
Antonio will be around
Also tomorrow. So if you want to chat, just let me know.
okay.
Thank you.